Okay, now for 2.7, we're to discuss inverse functions. First, let me start off by defining what a one-to-one function is. A one-to-one function f of x satisfies the following implication. If f of x1 is equal to f of x2, then x1 is equal to x2. It's a weird definition, but we'll kind of see why it's important in a second. First, let me say that, as an example, f of x equals 3x minus 2, a linear function, is one-to-one as it turns out. Any two x values you plug in will result in the same y value. That's really what this says. Well, any two x values that result in the same y value must be the same. That's what it says. If the y values are the same, then the x values must be the same. Okay? So I'm not going to convince you too much of that, but just notice if, let's say f of x is equal to 5, just as an example. Maybe 5 isn't a good example. Let's do 4. If f of 5 is equal to 4, if f of x is equal to 4, there we go, then this implies that x is equal to 2, because 2 times 3 is 6, minus 2 is 4. In other words, there's only one value, only one. No, it doesn't seem like we really have accomplished much here, but just kind of consider this example. And in fact, I think this is where this definition shines. It's best to understand when something is not one-to-one. So f of x equals x squared is not one-to-one. And here's why. If f of x is equal to, let's say, let's do the same thing, 4, what must x be? So what number squared gives you 4? There's two of them. Positive 2 and negative 2. There's not only one. Since there's not only one, this is not satisfied, because f of negative 2 is equal to f of 2. So f of 2 is equal to f of negative 2, but 2 is not equal to negative 2. So just kind of take a look at this. F of 2 is equal to f of negative 2, but those x values are not the same actually. So there we go. Okay, moving on, horizontal line test. If a horizontal line passes through the graph of a function more than once, then the function is not one-to-one. And here's a really good example of that. In fact, notice, just as a quick example off to the side here, if we graph f of x equals x squared, what does the graph look like? Well, it's an upward parabola like this we've seen before. And notice, almost every horizontal line you can think of will pass through the function, the graph of the function, more than once. So it's not a one-to-one function because it fails the horizontal line test. Good. Next, we'll now finally see what we want to discuss in this section, inverse functions. And I say a one-to-one function, f of x, has an inverse function, which is labeled f inverse of x, that satisfies the following. Composing f inverse with f in any order will only result in just x. Now what I want to say here is that f inverse and f undo each other. So let me just say f inverse undoes what f does. I think this is a fairly important statement that will help you understand more what inverse functions really are. They undo what the original function does, and we'll see a few examples of that right now. Alright, so now I start off with this example here. F of x is 1/2 x plus 4, and I claim that the inverse function is 2x minus 8. Now I don't say how I get this. We'll figure out how to find the inverse of a function pretty soon. You kind of see that over here, but I'll discuss that soon enough. But what I want to talk about is how do I know that it is an inverse? Well, remember what we need to satisfy. Composing them in any order results in only x. So let's do that. Let's take f inverse composed with f of x. That's f inverse of f of x. So f inverse of f says to plug f into f inverse. So f is 2x minus 8. So we're plugging f of x into f inverse. F of x is 1/2 x plus 4. If we distribute the 2, we get x plus 8 minus 8. Look at that. The 8's cancel and we indeed get x. And that's true. Good. So that means they're inverses. Again, we have to check in both orders. I'm only going to check in one order. I'll leave it as an exercise for you to check the other order. But something I want to show that I think will help understand what's going on. Remember what I said. F inverse undoes what F does. So let's just plug in some random numbers. These are totally random numbers that I'm just kind of making up off the top of my head. And I'm going to plug them in to F. Let's see what we get. In fact, just so it's a little easier to plug in because it's 1/2 x, I'm going to make one of them even. Well, most of them even. I'll also do one odd, so we'll see that. But let's see. So I want to plug -2 into F. So -2 plugged into F is what? -2 plugged into F is 1/2 of -2, which is -1, plus 4 is 3. Okay, plug in 3 into F, then we get 3/2 plus 4. 3/2 is 1/2. 1/2 plus 4 is 5/2, which is 11/2. Okay, now what? Well, now if we plug in 6, 6 times 1/2 is 3. 3 plus 4 is 7. And there we go. So what did F do? It turned these numbers into these numbers. So what is F inverse going to do you think? Very good question. What does F inverse do? It undoes whatever F did. So let's see if we can see that here. Plug in 3 into F inverse. Well, let's see. 3 times 2 is 6, minus 8 is -2. Plug in 11/2. 11/2 times 2 is 11, because the 2's cancel. 11 minus 8 is 3. Plug in 7. 7 times 2 is 14. 14 minus 8 is 6. Look at that. We get exactly what we started with for each of these. So indeed, F inverse undid what F did for each number one at a time, basically. And how we can check that is by what I did here. So if they compose to just give you x, then that means they undo each other, actually. So a better way of phrasing this isn't that F inverse is the inverse of this, but they're inverses of each other, really. Now, as far as the graph is concerned, we could graph these. They're going to be lines, but I just want to get this out of the way. Let me just say that the graph of F inverse of x is the same as the graph of f of x, only reflected about the line y equals x. So if you pick any point here, it's on the graph of f, so it's of the form x comma f of x. Okay, good. So this is the y value. But remember, f inverse undoes what f did. So the x and y values will be swapped for f of x, for f inverse. So if you swap x and y values, what that's really doing is reflecting across the line y equals x. So here, this x value will be the same as the y value we got over there. So if this is f of x, f inverse of f of x will just give you x. So where this point is of the form x comma f of x, this point will be of the form f of x comma x. I know that sounds a little funny, but this process that I've labeled out over here describes that in its entirety. So I say to find f inverse, you follow these following steps. There's 4 steps really, but I've condensed it into 2 steps. The main 2 steps are you let x equal f of y, and then you solve for y. Solve for y equals f inverse. So f inverse is going to be our y, basically. But in reality, the 4 steps are the following. Replace f of x with y, swap x's and y's, solve for y, and then finally replace y with f inverse. So let's see if we could follow these 4 steps. So the first thing is I want to replace y, or replace f of x with y, I should say, and then swap x's and y's. So we see why I wrote let x equal f of y, because all we're doing is replacing x with y and calling that x. So this is really the first step. But to do that, you can replace f of x with y and then swap x's and y's to get there. The next thing we want to do is solve for y. And we're going to call that f inverse. So solve for y in this case, we'll add 9 to the other side. we'll get x plus 9 is equal to 3y. Very good. Then divide both sides by 3, and we get that y is equal to x plus 9 all over 3. But remember, we're calling y f inverse. And you know what I'm going to do? I'm going to take advantage of this space I have over here, and I'm going to rewrite this a little differently. In this case, what can we do? This is all separate. We can actually split this up. It doesn't always happen, but in this case it does. If you split this up as x over 3 plus 9 over 3, x over 3 plus 9 over 3, x over 3 is 1/3 x, and 9 over 3 is just 3. There we go. So that's our inverse function. And you can just check by taking their composition and seeing that you get x. As an example, I'll just plug in some random number, let's say 10. When you plug in 10 into f, you get, let's see, 30 minus 9 is 21. So that means, just as an example, let me write e.g. for small example. If we plug in 10 into f, we get 30. Just some random number I picked. So if we're correct on this being f inverse, then that means plugging in 30 into f inverse will result in 10. It undoes what f did, right? Right. So let's plug in 30 into this. Notice 1/3 times 30 is what? 1/3 times 30 is 10, and then 10 plus 3 is, 30. It's 21. Jeez, my mistake. So plugging in 10 gives you 30 minus 9, which is 21. There we go. So plug in 21. There we go. 21 times 1/3 is 7. 7 plus 3 is 10. Perfect. So it worked with just some random number we picked. But if you want to check it works in general, just compose the functions. And there you go. So I'm going to do one more example of this, and that'll be it for 2.7. All right, so now for this example, I want to find the inverse function of this function. This, by the way, is called a fractional linear transformation. We don't really need to know that, though. If you want, you could, I guess, look into it. I'm going to generalize this as it turns out, just because I don't want to leave you hanging with only one example. I want to generalize it, which is kind of nice. But we'll do that after the fact. First, let's just follow the steps from before. So the steps from before, remember there are two main steps. The first step is to let x equal f of y. So if we do that, that means x is going to be equal to f of y. This is f of x. F of y is just replacing all x's with y's. So it's 6y plus 4 over 4y plus 5. And that's how that goes. Second step is to solve for y and call it f inverse of x. So to solve for y is going to be a little weird, but I'm going to cross multiply. Things simple enough so far. Then we are going to distribute the x on the left, and I'll get 4xy plus 5x is equal to 6y plus 4. And remember, we want to solve for y. So let's move all y's to one side and all non-y's to the other. So subtract 6y to the left and subtract 5x to the right. What we're left with now is this 4xy minus 6y. They're not entirely like terms. They have y in common, so we can actually factor that out, which may not be very obvious of a thing to do. But think of it like this. Y is in two locations up to this point, and then if you factor y out, now we only have one y instead of two y, so it's easier to manage. Over here on this side, we just get negative 5x plus 4. That's fine. And now finally, to get y by itself, what do? We divide both sides by 4x minus 6. And we get y, but what are we calling y? We're calling y f inverse of x. Perfect. So now we have f inverse of x as our final answer is equal to what? Well, it's equal to negative 5x plus 4 over 4x minus 6. That's our answer. Beautiful. Now I want to generalize this, so let me just say the following. In general, for f of x equals ax plus b over cx plus d, f inverse of x is equal to what? Well, notice there was nothing special about these numbers, 6, 4, and 5. These numbers are the same, but they're both 4, so it's a little hard to see what happens. But I kind of just want to tell you, but I guess I'll prove it to you. So let's do the same thing we did here, but in general. So I hope we have enough space. So the first step is we're going to let x equal f of y. So it's ay plus b over cy plus d. The second step is to solve for y, and we'll do so by cross multiplying just as we did over there. Cy plus d all multiplied by x. Then we'll distribute the x just like we did over there. So we get cxy plus dx equals ay plus b. Moving all y's to one side and all x's to the other, we get cxy minus ay is equal to negative dx plus b. Perfect. Factoring y out on the left gives us y all multiplied to cx minus a. And then finally, dividing by cx minus a gives us the following. Remember, y is f inverse of x. So f inverse of x is equal to negative dx plus b all over cx minus a. What's really nice about this is that there is a pattern. So if you're given a linear fractional transformation, which is a function that's a fraction of linear expressions, so ax plus b over cx plus d, let's say, all you really need to do, if you look here, all we're really doing is looking at these numbers here, a and d, negating and swapping them. So if you negate them and swap them, they're in opposite locations now, and they're both negative. So take a look at this. If we look at 6 and 5 and did our negate swap trick, we get exactly that. We get negative 5x plus 4 over 4x minus 6. So there's like no work to do. We can just generalize it, and it'll create basically a really quick shortcut. Of course, only for these types of functions. And again, that's really all I wanted to say for 2.7. Yeah, it's a pretty loaded section in my opinion, but it wasn't that bad. We handled it in a nice way. Hope you enjoyed it. I only did a few problems here. There are a few homework problems scattered out like I always do, so if you look back at the previous sections, there are homework problems there as well. And that's actually it for chapter 2. We're going to move on to chapter 3 in the next coming videos, and I'll see you guys then. Thanks for watching.